Let's start by introducing to you this handsome moustache guy. Who knows who this guy is? Come on. Well, Nikola Tesla. Some already shout out the name. How do you all know it's Nikola Tesla? This is his brother. No lah, joking. This is Nikola Tesla. Right? How do you know it's him? Oh, you're all very good. So I'm going to teach you AC. And AC is invented by this guy. And he's not just any other guy. Alright? You are stepping into a rich piece of scientific history. And by the way, Nikola Tesla, if you don't know, also did radio, radar, X-rays, built the first hydroelectric plant, patented transistors 100 years before they were actually built, first person to record radio waves from outer space, created ball lightning 100 years before modern scientists, created neon lighting, created remote control. Modern electric motor also belongs to him. Wireless communications, spoke 8 languages. No, at this point I want to say something. You all are my second group. You all are my second group. I show all this, nobody wow one. Nobody wow. Then I show this one, everybody wow. Hey, hello, everything on top is 10 times more difficult than this. I feel sad. So this front one is 10 times more difficult than this. This one I also can do if I spend enough time. But this one, I put my whole lifetime times 10 also maybe cannot do. Because you want to be the first 100 years before your time. This guy is a genius. This guy is a genius. Right? So what you're learning in the next 3 lectures is a slice of his genius. It's just a slice, tiny, I think only 0.1%. 0.1%. Okay? But he's a genius. And since we're talking about geniuses, there are actually 3 kinds of geniuses in this world. Okay, let me categorize them for you. 1, those who call themselves geniuses. 2, those that other people call a genius. And 3, the genius that other geniuses call genius. He is the third type. Alright? And we are stepping into 0.1% of his skills. Right? So sit up, listen, and pay respect. Alright? He's dead so pay our respects. Right, if you look at your LO, your learning outcomes, there are 3 parts, right? I categorize them into 3 parts for you. There are a lot of words, but don't worry. Today we're going to cover AB, CD, a little bit, right? AB and CD, a little bit of CD. AB we'll cover very quickly. So AB is just the introduction of DC compared to what AC is. And then we'll introduce some terms and waveforms. So all these are just catch up. DC versus AC. So the definition for DC is that it flows in one direction. Yes, like the band, it flows in one direction. Right? So this is definitely DC. This is the DC that you're used to. Look at this on the right. Don't look at your notes yet. This is a bit curvy. Is this a DC? And the answer is yes. The answer is yes. Why? Because the current has not yet changed direction. It has increased and decreased, but it's still in the same direction. So if you imagine this as a road, if you're standing in front of a road, sometimes there are more cars, sometimes there's less cars, but the road always moves in the same direction. It is one direction. If you have your road suddenly, sometimes the car moves in opposite direction, then it's like a silver Mercedes. Okay, nobody caught that. Okay, never mind. Because it's the opposite direction. Okay, never mind. Okay, never mind. Forget it. For a road to look like an AC, you must have sometimes the car come from this side, sometimes come from the other side. Okay, Ken? Okay, moving on. Forget it. Right, AC. There are a few types of ACs, right? ACs, as long as move direction, it must go below 0. That means the current can read as a negative current, right? It is an AC. So there's a few types that are very common to you. The first would be the wavy kind, like this. This is what we call the sinusoidal AC. Remember the name is sinusoidal, right? Then you have the square wave, which looks just like a boxes, up and down. And then you have the triangular ones, right? But the triangular ones appears almost never in your A-levels. The first two appears quite often. So this is where we will focus on. Okay, today I will introduce the square one to you. If we have time, we also do the curvy ones, all right? Boring stuff, you already should know. If you don't know, then you should psh yourself, all right? First up, right, you have a sinusoidal wave. Peak is called I naught. The period, peak to peak, right? The peak to peak current is from the top, the crest, to the trough. That's it, right? So a few other. So now let me show to you what AC that I realized in my years of teaching. I need to give a visual representation, right? So if you look at a sinusoidal wave like this, you start off at this point. You have no current, all right? All eyes on the screen, no current, because I put in effort for this. So. Your current increases, you see the arrow becomes thicker. Current increases, some more arrow becomes thicker. Current increases, some more arrow becomes thicker. Current decreases, arrow becomes less thick, but in the same direction. Current decreases, but in the same direction. Current goes to 0, then current changes direction. You don't know how much work when you do it. So since so much work has went into it, just one more time. Right? Okay, very quickly at hyper speed now. There you go, okay? That is basically what an AC is like. Alright, got a sensing of it? Small, bigger, bigger, smaller, smaller, 0, opposite direction, negative direction maximum, come back to 0. Alright? Right, some terms. Well, you need to know the wave equation, how to write a wave equation. I know in CT1, some of you made a mistake here, right? Don't make the same mistake. It's required in this chapter. So if you have any issues with waves and how to write waves in the form of equation, you need to brush it up. But you know it's usually written in this form. You have the maximum as the I naught, and then the sine omega t as the sinusoidal part of it. Okay, period, frequency, angular frequency. Right? Note that here it's called angular frequency, not angular velocity. Right? I know omega in circular motion you call it angular velocity. But ever since then, you've always called it angular frequency in your SHM and now. Right? You've always called it angular frequency. So do note the difference. Okay? Otherwise, it's used, the equation-wise is the same. It's 2 pi over t, 2 pi f, not an issue. Peak current, not an issue. It means the maximum current that you have. Peak to peak current means the top to the bottom. That's it. All right, simple stuff. And we are done with the first part. Yay! Wow, imagine if we move the next 2 parts in the same amount of time, we'll be done by the next 10 minutes. But no, unfortunately cannot. Next 2 parts are a little bit harder. So you bear with me. It's going to be a little bit more intense, all right? But I try my best really to make it simpler for you. First, we need to talk about power dissipation in the resistor and the mean square current. Then I need to introduce to you what's the root mean square current and what's the average current. These are the few terms I need you to know. So I need you to input in your brain now. By the end of the next 15 minutes, you need to know what is a mean square current. And by the end of this lecture, you must know what is a root mean square current. All right? Right. Let's go. Power is dissipated in a resistor, we know, right? As we showed just now in the AC that I showed you, whichever direction the current flows, there will be power dissipated. Correct? Right? It converts the energy entirely into heat, okay, for a pure resistor. And we can be just more than this. So this is something that turns electricity energy into heat. This is something that turns electricity energy into heat and light. But whatever it is, the energy converter is called the power converter. Okay? So power conversion for DC is simple. We know it's called E squared over R. By now, if you don't know, then you probably has not been attending lectures since forever. No. That wasn't a joke. That was a statement. But we have a problem here. In an AC, the current goes up and down, right? In a DC, the current stays constant. So when you connect an object, an electrical component to a DC circuit, you can tell very easily whether this object can withstand that circuit or not. You can calculate what V is there. You know that if you look at the object, you say, oh, it's used for 10 volts. Oh, the circuit has 10 volts. Connect it, not an issue. Right? The thing can withstand 2 amps. Oh, 2 amperes. The circuit gives you 2 amperes. I can connect it, no issue. But in the AC, the current moves. How do you know what equipment to connect to what circuit? Which is why this chapter is for us to introduce to you how to think about this. All right? So one of the ways that scientists and physicists decided at the end is to use power rating as one of the ways, right? The power rating of the equipment. So for an AC, this is obviously the issue. Let me illustrate that to you. When the current is small, these arrows that you have all around is the heat dissipated. The heat dissipated is small. Current becomes bigger, heat dissipated is bigger. Current becomes even bigger, heat dissipated is even bigger. Go down, go down, go down, 0. Opposite direction, heat too small, medium, large, medium, small. Okay, by now you should be bored, right? But you see the inherent problem. There are multiple power ratings at multiple times. How do you decide what to call it? Maximum is a possible way, but it's not accurate because it does not tell you how much power you do over time, right? So that is what we want to do, right? You have it instantaneously, right? You could maybe, if you only care about the instantaneous power, then the maximum power will make sense as suggested by your friend, right? But it is not, because that will not allow you to know how fast you can charge your phone. Okay? So one way is to find the average power. One way, because we want to know how much energy is given to, let's say your phone needs about 100 joules of energy, right? 100 joules of energy, but you only know the maximum is 200, like 2 watts. You don't know how long you'll take your phone to charge. So you have to find the average power. So all you have to do is take the average power times the time. You can find how long it takes to charge up your phone, for example. Okay? But there's a problem again. How do you find average power for an AC circuit? How do you find that average power? So today I'm going to teach you. To find average power, you just pick a bracket around I squared R, then like, okay. Or you can take a bracket around V squared over R. And since R is a constant, you can take it outside. And then you have, what you end up with is the I squared R. Okay, the I squared bracket. The bracket is called the mean. All right, so if you look at it mathematically, what you do is you square it, then you mean it. Okay, you square it, then you mean it. Right? But when you say it out and you write it down, it's called the mean square current. Okay, so you mean it first, then you square it. You know the difference? Mathematically, you square it, then you mean it. In language, we mean it, then we square it. All right? So I introduced to you the first thing that could help us discover what is, or rather calculate what is the average power. It's the mean of the square of the current. We call the mean square current. Okay? Why is this useful? It is definitely more useful than the mean current, right? And to show you, it's not the same. The mean current for a sinusoidal wave, can you tell where it is? It is here. Can you see the red one that just appeared? Okay? The blinking one. Right, that is the mean current. You agree? That is the mean current. Yes, it's 0. So if you connect an AC to a supply, AC to an object, You know that the mean current is 0. Does it mean that the mean power is 0? No, it cannot be, right? Because the power is obviously there. When you send current through, it must produce power. So mean current doesn't make sense anymore. If you use a mean current in an AC, you usually get it wrong. Okay? What is important is the mean square current, because P equals I squared R. Okay? But here, note, I cheated. I put the square root of the mean square current. Why? Because I cannot draw I square on the I graph. So I must square it back again. Right? Which means later I need to show to you what is a root mean square current. Okay? Can? This part that just appeared is to show that the square mean current is not the mean square current. Okay? Can? Questions at this point? Right, example 1. Okay, example 1 is just to hit the ball on a home run. It's very easy. Current is there, asks you to find the first express. The hardest part is just part A, the rest is simple, right? Express this in the equation. So you know that I equals to I naught sine omega t. This is obviously a sine curve. I naught is 1.2. Omega you can find from this 0.02 times. Booms, there you have. Easy peasy. Okay? Any issues with the first part? Okay? The others are also pretty simple. Right? You sub in the, once you have this equation, you sub in the time, you get your answers. Okay? At this point, I want to remind some of you, right? Here is sine 0.5 pi. So the mode you use in your calculator must be what mode? Very good. You'll learn your mistake. Right. Same for next few parts. Okay, all the answers are given. So this example is to hit home the message. How do you find the average power if you have a varying current? Okay, I showed you the method, but still I haven't taught you how to exactly do it. Okay. So here it is. Here it is. To find the root mean square current and the average power, right, you have to use this equation. Right, because remember, mean square, how do you find? Mathematically, this is what needs to be done. You take the I square graph, you integrate it between 2 times over, well, integrate it with time, find the 2 extremes divided by the total time you divide it from. Obviously, this is crystal clear to everyone, right? Not. Right? Obviously, it's not clear, right? Unless you're like me. Which you are. Okay lah. Sorry. But let me try to explain it clear to you, right? I promise you I want to make it clear to you because I know this is a difficult point, right? I especially put this kind of bright signatures, signboards here. What does this actually mean? What it means is that you take the I graph, I over t, you square it, then you integrate it over time. So I'm very distracted when you're looking at the phone and comparing it. I'm trying to help you. Please help yourself. Okay? Right. I square. So you take the area under the I square graph over time and you calculate the total area. Right? That's what it means over here. The math symbols means you take the I square graph, plot it versus time, find the area under it. Right. So just now I gave you a teaser of the mean square current. Now I need to introduce to you what's a root mean square current. Wow, another thing coming into your brain. So mean square current, what do we do? You square it and then you mean it. If it's a root mean square current, what do? You square it, you mean it, then you root it. So I'm going to show you visually again what it means. Root, mean, square, current. That is how you say it. But what you do mathematically is you take the current, you square it, you mean it, and then you root it. Okay, Ken? Very visually appealing. One more time. Right? Serious. You need to know, if not root mean square, you mean, then you root, then you square it, also wrong. Okay? You must have a correct order. Okay? Right. Some other information. This is for you to know, and this is actually what you have been assuming all your life. Right? So this I'll just very briefly breeze through, which is that the V and I are always in phase for a pure resistor. There are situations where it's not, but until now and almost completely in A levels, except for this chapter, everything is a pure resistor. All right. This chapter there'll be one thing that is not a pure resistor. I'll tell you later on. All right. So just note this. If they are in phase, they'll look like this. In phase, they'll both reach maximum at the same time. They'll both reach 0 at the same time. They'll both reach halfway at the same time. Okay, which allows us to write VRMS equals IRMS. The maximum V naught is just the maximum I naught times R. Okay. Can? Oh, still have time. Lucky. Any questions at this point? Okay, good. Okay, so what I need you to take away from this page is these two equations. VRMS equals RMS times R, V naught equals to I naught R. Right, finally I can jump into what I've been promising you since the start. Oh, how do you find the average power in a resistor? I gave you this equation, and I teach you a lot of things so that you can then understand this. We say that the average power is the mean square current times R. But mean square current is not a useful way to represent it. Why? Because the mean square current means whatever current you read, you must square it back. Because in your iPhone, in your phones, I'm a Samsung user, so in your Samsung phone, you check the labels. It says the current it can take is something ampere. It never ever says something square, ampere square, never. That's why you cannot, this is not good enough, right? For the communication of the science, it's good to then have something that is comparable to a DC current, which is this. Right? So you just square root back this, which gives us the root mean square current. So average power is now the root mean square current squared. That's a mouthful, right? Say again, I heard a what, very good. So if you don't know what, just say what, then I will respond, okay? Mean square current times R gives you the average power, agree? Yes. When you square root the mean square current, what do you get? You get the root mean square current. Which means, if you take the root mean square current squared, it's like a tongue twister, root mean square current squared times R, you get the average power. Do you agree? Yes. Also, basically, the root mean square current is just this, but instead of writing a hat, a bracket, and a square, we just write IRMS. Much easier. Okay, so I introduce to you now IRMS and what is it exactly already. Okay, Ken? Yes. Coming up. Coming right up. Coming right up. Yeah, it's like my whole lecture until now is a teaser, right? Just keep telling it's coming right up. Right, it's really coming right up, okay? Once you know this, you can then also express your power in terms of VRMS, RMS, VRMS square over R. Okay, why? There are some equipment, maybe I answer it now, since you brought it up. There are some equipment that you have, like your portable radio. How many of you have a portable radio at home? About this size? Okay, no, how many of you still listen to radio? All right, yeah, sorry, age gap. How many of you have those handheld fans? Handheld fans. It is powered by a battery, yes? Powered by a battery. How many of you have a handheld fan that can be plugged into the wall? Don't have? Okay, my point is, there are some equipment, like your portable radio, or your handheld equipment that can be either used via battery, which is a DC circuit, or via the means, the power output that you have in the walls. Why do we need to do all this? Because when you read that, right, it tells you what battery to use. That gives you the voltage you need and the current you need. But you then, as engineer, well, your engineers do it for you, so you don't need to know. But your engineers on the background have decided, oh, since this requires this amount of voltage, this amount of current, what do we need to do? How do we convert that current that you have in the wall into a current that you can use? Right? That's what they did. Right? And after this chapter, you should know how that is done. Okay? And to actually communicate that properly, we use what we call an IRMS current, because that is the equivalent of the DC current. So for example, so I finish my example. Your battery uses, for example, a 6 ampere current, a few batteries to give you a 6 ampere current. If you plug it into the wall, you want to convert that power from the wall into an IRMS current of 6 ampere. And then convert that to a DC for you. Okay, Ken? That is what I can say in as few words as I can. I know it's not completely clear, so bear with me for the next 2 weeks. 2 more lectures. Okay? Right. So now, we come to the definition of the root mean square current. Very long. I hope maybe this definition could help you understand what you're asking also. The root mean square value of a current, of an AC current, is defined to be the value of the DC that, if used to replace the AC, will generate the same amount of heat in the resistor. That means if previously I used a DC, the power generated was 10 watts. I connect it to an AC now, and it's still producing 10 watts. The IRMS of that AC has the same current as my DC. Clear? I say it another way. I have an object that's using an AC now. It has a certain IRMS value. I don't know what it is. I take the same object. I now connect it to a DC. And if it's producing the same amount of heat, and I check the DC current, it is 2 amperes. And I can say, the IRMS value of the AC is 2 amperes. Clear? Right, but I know this definition is tough, so I'm going to give you some time to try to memorize it. Okay, I'm going to give you 30 seconds and memorize it and understand it. Understand it already is easier to memorize. Okay? Now that you understood it, memorize it. 30 seconds, go. Next lecture. All right. I saw some of you practicing your memories. If you can, then it's good for you, right? But usually you need to cover up thing, then write it down, then see what you missed out. Okay. If you can just stare and get it, good for you. But let me try also. Okay. So now I show you. I can do it also without looking. Actually, it's very hard. As you get older, it gets harder. But I show you that it can be done. If I can do it, you can do it. The root mean square value of AC current is the value of the DC current, if used to replace the AC, will produce the same power as the AC current. What did I not say? The steady, is it? Steady, yeah. What else? Generate heat. Can. Because it's just the meaning is the same. So definitions, as you hit enough of the correct points, will be correct. Okay? But you must, with experience, know what is correct. So one more time. The root mean square value of the AC current is the value of the DC if used to replace the AC, steady DC. If used to replace the AC, will produce the same amount of heat as the AC, average power as the AC. Okay? Right. Oof. I threw you some terms, mean square current, root mean square current, average power. I show you how they are represented, how it's linked together. Now I need to show you how to calculate it. Actually, just now in the meantime, just now a student asked me, why do we need to use AC anyway? That one really I need to tell you, I can only tell you next week. Sorry, this Friday, next lecture. All right. So today I'm going to try to cover this for you, and we probably don't have time for the sinusoidal AC because of time, but this is what we're going to cover. I'm going to cover IRMS now for you, 4.1. But I can only give one example of it. So 4.2 is actually an example of an IRMS. Okay, 4.2 and 4.3 are actually examples of IRMS. Write it down. Starting with IRMS for square values. Root mean square current for square waves. If you look at the left, this is a DC, right? You can calculate the power. That's question example 2A. Right? Calculate it, it's not difficult. It's given as 20 watts. It's given in your notes. Right, I printed everything out for you so they can just listen and look at me. Okay. Next, if you do the same for the AC current, you realize that it's the same thing. Right, the power is exactly 20 watts. Right, whether it is positive, it's 2 square. If it's negative, it's negative 2 squared, which also gives you positive 4. But why is this so? Watch. When you square the current, look at the graphs, they become the same. So naturally, the powers dissipated in both of them must be the same, despite one being a DC and the other one being an AC. Okay? Can? So what can you say about this AC here on the right hand side? What can you say about the root mean square current of this AC here? 1, 2, 3, the value is 2. It's the same, yes, it's 2. Alright, can? That is what I need from this example from you. Alright, now you understood the definition and you see it applied in real life. So the IRMS of this is 2. Done. Now we try a different square wave. This square wave a little bit harder. Okay? Express the mean square current in the resistor in terms of I1 and I2. So recall, what is mean square current? In the mean square current, what do you do first? You square it, then you mean it. So if you square current, right, you break it down into 2 parts. You take this part, you square it. You take this part, you square it. Once you square it, you get I1 square, I2 square. And you want to take average. How do you mean it? So I give you this example. If I give you 3 apples for 3 days and 1 apple for 1 day, what's the average number of apples you have per day? 3 apples for 3 days and 1 apple for 1 day. So out of the 4 days, you receive how many apples? Oh, sorry, that means my language not clear. 3 apples per day for 3 days. 3 apples per day for 3 days and 1 apple for another 1 day. Over the 4 days, how many apples you got? What's the average number of apples per day? 2.5, right? That's what you do here, same thing. This is what happened here. Can you see that? Can you see that? I square it, Forget the squaring part. I'm talking about how do you take the mean part. Okay, so I show you to you now visually. Just now was mathematically, verbally. Square it, what do you get? You get this. Mean it. How do you mean it? You look deeply into the eyes and say it sincerely. Right, okay, it's because it's near the end, I know you're tired, I also tired. So that was a last lame joke of this lecture here. No more. I try. I'm very serious one, okay? Mean it, how do you mean it? You take the area on top and bring it below. If the areas are the same, the red line is the mean. If I move the red line up, if I move this red line up, the area on top will be less than the area below if I move the red line up. Agree? Yeah, so this red line is the mean because the area on top and the area below are the same. Let me give you another example because I realized this part was difficult. After the first lecture, I went to ask my students. They say, oh, this part I don't understand. So I give you another example. Okay? How do you mean it? 10 apples in one day, 5 apples in another day, 0 apples. What's the mean? Mean is 5. You do it very easy because you took 10 plus 5, 15 divided by 3, 5. But what have you exactly done? What have you done? You have actually taken this area and slotted it into this area. They are exactly the same so that you have a mean like this. Correct or not? That's what you have done graphically. Okay? Why I use graphically? Because later on there are some things that you cannot do with simple numbers. Like these are simple numbers. Try this. What's the mean number of apples? You all are like super computers. Huh? But for me, I like to play Tetris. This is very satisfying. Right? You get a mean value of 5 because the areas are the same. That's why I must choose areas above the line to be the same as the areas below the line. Okay, Ken? Ken, huh? Oh, this guy, yes, please. Okay, continue. So now you know why I need to have the same areas. Okay? Done. Next, what do we do? Right? We found the mean square current. They ask you to find the average power. Just substitute in the values. Super easy. Right? Part B is like, you can get part A, part B is like a walk in the park. It's like your Sec 2, Sec 3 questions, right? The equation is already given, plug in the numbers. Unless you key wrongly, like your fingers are a bit fatter. You should practice. With practice, it becomes better. Next, they ask you, find the root mean square current. Find the root mean square current. So you can find it easily doing this, right? You found the mean square current already, right? The equation. All you have to do is take that equation and square root it. So plug in the numbers, you can find the root mean square current. Okay? So I'm going to show you now how to find the root mean square current. Root mean square, what do you do first? Square it. Do you agree this is the graph you will get? What do you do next? You look into the eyes, what? Mean it. Then what do you do next? You root it. Okay? So you see, you start with this graph. You mentally draw the I-square graph. You then mentally mean the I-square graph. Then you mentally square it back to draw the root mean square current. In a working, usually this part doesn't appear. Usually it doesn't appear. You can be it's a working on the sidelines, right? Because what we care is only the final answer. Okay, Ken? Right? So I show you how to root mean square something. And just for comparison, right? I started earlier today saying the mean current and the root mean square current is not the same. So here I prove it beyond doubt to you. If I take the mean of this current, it's only 2.5. Right? You have 4 for 3/4 of the time, -2 for 1/4 of the time. You average out is 2.5. So you see, 2.5 is not equal to the root mean square current. The mean current is not a useful indicator of how much power it can produce. The root mean square current is. Okay? So I hope I answered your question a little bit. Not yet. And one more question. Together we will show you why we are doing all this. Okay, so next lesson we should do all this. Do we have time? Oh, we have. Let's do it for the sinusoidal wave. Okay? I'm going to tell you why we need to do it. Because square is so easy. This equation is given by this. Agree? Agree? No, you're tired. I know you're tired. Bear with me. I'll repeat this again, right? Because I'm going to go a little bit fast. When you square it, what do you get? You get this equation. Do you agree? Okay. Do you know that this equation is equal to this? Double angle formula. Correct? Very good. Why do I need to do that? Because when I was your age, when my teachers were your age, we don't have a graphic calculator. So when you square this graph, how do you draw it? How do you draw the sine square graph? Now you're just graphic calculator. So I show you. You start with a cosine graph. Start with a cosine graph. You double the frequency. You get this. You put it into a negative. You get this. Do you learn this in the secondary school? Graph manipulation? Please say yes, no? Yes? Yes. Yes or no? No. Yes. Conflicting signals. It's a very good skill to learn. Please learn it. Please learn it. It's really important. Some of the exam questions assume you know it. Next, what do? You add 1 to this. The amount of work this has gone into. What do you do next? You bracket it out. You multiply by half I naught square. And this whole thing is a constant. So you start with this. It's either go lower or higher. Doesn't matter. The same shape will happen. So essentially what I'm trying to do, I'm trying to tell you that your sine square graph will look like this. Follow? I have showed you why your sine square graph is not a McDonald's sign. Pointy bottoms. Physics, we like smooth bottoms. You all don't interpret it wrongly. Right? For a sine square graph, it needs to be smooth, right? Not pointy. I don't know what you're thinking. So, let's do the drill. Root mean square current, how do you find it? First you square it, you get this. What do you do next? Then you mean it. How do you mean it? Find the line where the area above is equal to the area below. A lot of work went into that, man. Those of you who have done PW, which is some of you, the amount of work is required is crazy. Anyway. Alright, so that, mood so high that I say PW. It's like a taboo word. Anyway. But when you mean it, watch this. The area here, that line is just nicely half of the maximum value. Can you see? Oh, it's just nicely half. And when you root it, when you root half I naught square, what do you get? You root half I naught square, what do you get? You get I naught over square root 2. I have demonstrated to you why the root mean square value of a sinusoidal wave is I over square root 2. Okay? Okay? Say okay. All right. And that brings me to the end of today. Right? Next lecture, we'll recap this a little bit and I'll talk to you the rest of the blah, blah, blah. Okay? Thank you very much. Bye-bye.